All right. I want to take a little bit of time to review and go over sign conventions, because I realize that some of the, like, change in, I know that this chapter is predominantly based on entropy, but we a lot of times use change in H in here as well to find Gibbs free energy. So I really want to kind of review all the sign conventions, what a positive change in H means, what a negative change in H. We're going to continue doing change in G stuff today. Okay. What does a positive change in H tell us? Tells us a few things. Okay? Tells us the endothermic reaction. It also tells us that it's unfavorable. I'm not going to say spontaneous, because you could have a favorable reaction not be spontaneous. Okay, what does negative mean? And this is typically usually favorable. That's not actually favorable, is it? Here we go again. Is that right? Okay? What does a positive change in S tell us? Now, I'm not specifically saying surrounding system anything, just entropy. Just entropy. Is it more disordered? Okay, so it would become more disordered. Now, I could say less ordered, but I'm not going to put both of them up there because I don't want to confuse you. Is this favorable or not? Yes. Okay, a negative change in S. Less disorder. I could also say it's becoming more ordered. Okay, now, change in G, the equation for change in G, the reason why it's so important is because just because I'm exothermic doesn't mean I'm spontaneous. And just because I am increasing in disorder doesn't mean I'm favorable, because I have both of these things going on. Because usually when I'm talking about this, I'm talking about the system, and this determines the surroundings. And that's why the change in G equation is so valuable, is because it takes the two things that favorability hinges on and puts them into one equation. If you have a positive change in G, it's spontaneous. Now, it could be spontaneous and not be fast. So you would need to add the kinetics idea concepts to this as well. What?
Should be
Non, you're right. You're right. I wasn't thinking.
I just remember that it's opposite of G passes.
And if it's negative, it's spontaneous. And I gave you the chart the other day that said, okay, these two things go into here. If it's negative H, positive S, always spontaneous, because you're taking two favorable things and putting them in the same equation. If it's positive H and negative S, you're taking two unfavorable things and putting them in here, you're going to get an unfavorable or unspontaneous reaction. If you have opposites, one is favorable and one is unfavorable, then it depends on what? Temperature. At a certain temperature it will be favorable, and at a dip lower temperature or the opposite of that will be unfavorable. Okay, that's what that chart was that I gave you yesterday. Right? So then there was two ways to figure out whether it was spontaneous. One way was to use the change in G equation. What was the other way?
H was negative and
No, that's part of this way. What's the other way to figure out if it's spontaneous or not? There are two ways. The entropy of the universe is positive. There are two ways to look at it because there's a relationship between this and this. If you remember, S of the universe is equal to negative change in G over T, correct? That's the relationship between these two things. If this is negative, it's not negative, is it? Hold on. What did I give you? I don't remember. I'm pretty sure it's not negative.
That is negative.
Oh, yep, you're right. Yep. The reason why is because a negative change in G is spontaneous, so when I put the negative in with the negative, it'll give me a positive change in S of the universe, which is spontaneous. That makes sense? All right. Now, what did I say was the primarily determining, what is the primary determining factor? Whew. What is the primary determining factor for the system? What determines if the system entropy is favorable? No, that's surroundings. I had you guys write it the other day. That's for surroundings. What about the system? That's what exothermicity is. I had you write it down. I swear.
primarily equal positional probability.
Positional probability.
Yeah, I did right.
Okay.
Real.
Basically, order or disorder of the system is what positional probability is talking about. Okay? So, the primary determining factor for the system is how many positions it has. The more positions, the more disorder it will be, and the more favorable it will be. The reason why we said the surroundings is dependent primarily on exothermicity is because if the system is exothermic, it gives energy to the surroundings, making the surroundings faster, more energetic, and more what? Disordered. Okay? So, those are the two primary things for determining the entropy of the universe. Positional probability, okay, more disorder, and exothermicity, because we always are going to be studying the system standpoint, and if we know what's happening in the system, the opposite's happening to the surroundings. Right. That's kind of a crash course of the first 5 days. So, let's do today. Any questions quickly?
How to use the chart fact above the two.
What was that? So, really the goal of today is we're going to talk about the 3 ways that you can figure out change in G. I kind of already gave you one. There are 2 others. Basically, what Gibbs free energy is basically taking the 2 factors that determine favorability, put them into one equation so that I can just look at one sign convention and not have to deal with, oh, is S and H the correct signs? Or if they're opposite signs, will it be spontaneous or not? So the idea of Gibbs free energy is to take the two things that determine spontaneity, put them in one, so you're just dealing with one sign convention and not dealing so much with two. Okay? So that's really what Gibbs free energy is dealing with. So the first way to calculate Gibbs free energy, we've kind of already talked about a little bit, is using this equation. This one's probably the most difficult from a work standpoint. Well, I should say probably the busiest. It's going to take the most amount of time. I wouldn't call it overly difficult. The reason why I say it's the busiest is because we have to calculate change in S, then calculate change in H, then calculate change in S, plug them in, convert their units, and solve. So, how do we find change in H? Products over reactants, or divided by, or products minus reactants, and where are we going to get those numbers? From the appendix. If you remember, that was the formation numbers.
820.
And so the products you're forming and the reactants you're doing the opposite of forming. That's why it's products minus reactants. So let's all get to your appendixes. Hopefully it's not malfunctioning. Okay. So, don't forget the coefficients. So I got one product. Somebody give me what the enthalpy value of SO3 as a gas is. -396. And it is kilojoules per mole for the unit of H. You're going to want to keep those units straight when you're doing these, and I'll explain why in a sec. Minus reactants. I've got 2 moles of SO2. And the value for that is
-297.
okay, I don't know if you remember this, but we got a lone element. Well, it's in its elemental natural state. It has an enthalpy of formation of
0.
All right, plug in your calculators, tell me what you get. Okay, what's the unit?
Kilojoules per mole.
Okay, well, the moles are going to cancel out. It's just kilojoules. Okay, now quickly, just to help you get some practice on signs here, is this favorable or not? Just talking about H. See a head nod from Annie.
There it is.
Okay, now let's figure out if the S is favorable. Okay, same appendix, different column, different units. What do we got for SO2? SO3, yep.
257.
The units are different, so be careful. Okay, SO2.
248.
Okay, I'm going to use this time to kind of explain one thing to you. I don't know if I've ever done that yet. If you look, we got SO2 and SO3. Okay, something that's important to note, that the more complex the molecule is, the more disordered it is. So because this has one more oxygen, it's a more complicated molecule. Okay, it could potentially have some more positions with its structure. Okay, so notice that it has a slightly higher entropy value than SO2. Okay, so complexity, the more complex the molecule is, the more disordered it will probably be. Okay, now this is not going to be 0. It's only 0 for H. It's 205. Okay? And Zolf, what do you get?
Negative 187
Units are
joules.
per Kelvin. And you're going to see why it's per Kelvin, because the temperature here will cancel the kelvins up. Now, is this a favorable or unfavorable situation for entropy? Unfavorable, okay. So, these are opposing each other. So the primary determining factor on whether or not this will be a spontaneous reaction then comes down to temperature. Okay? Now, let's find the change of G, but I want to make a little note here. Different units. And we're adding and subtracting here, so they need to be the same. So it doesn't matter if you convert kilojoules to joules or joules to kilojoules, but you must do one of the two. Okay, I'm just going to convert those kilojoules to joules. I think it's just a little simpler, but that's just my personal preference. Okay, so it'll be negative. Did I say kilojoules to joules?
Yes.
I meant joules to kilojoules. Oh. Well, what do you prefer? You guys would rather do kilojoules to joules? Okay, what did we say the temperature was here?
298.
298. And that's going to be Kelvin. I should write that in there. Yep. So those two negatives will cancel each other out, so we'll have a positive and a negative section. When you plug in and you solve, you get what?
Negative 14,000. 142,000.
Say it again. 140,000?
Yeah, basically.
I have the answer in kilojoules, so. Since all these are 3 sig phase, we'll just go with that. So. Favorable? Or I mean spontaneous or not?
No. You want a positive G, right?
Nope.
Negative G.
So it's spontaneous. Does this mean that it's going to be spontaneous at all temperatures? No. My guess is that it would be unspontaneous at a higher temperature. Okay? Questions on this? The key thing that is mistaken usually is units. Okay? Second method. Gibbs free energy is actually a state function. Do you guys remember what a state function is?
It's non-linear, or does it?
What'd you say?
Path independent.
Path independent.
Yeah.
So, if the path does not matter, we can use Hess's law. Well, okay. Hess's law, you can't. Hess's law usually deals with the path. But even if you use a path independent one, you could still do Hess's law to figure out the change in G. You guys remember Hess's law? Lock it in, baby.
I don't remember. Oh, that's
Does that ring a bell at least? Okay? So this is our end goal.
yeah.
We can flip them. We can multiply by coefficients. We just have to make sure we do the same thing to the change in G value. Okay, so if I want carbon as diamond, solid form, looks like it's here, nowhere else, on the same side as the correct coefficient, you would lock it in, baby.
The other one you flip.
The other one you gotta flip. So if you flip, you gotta do what to the sign? Okay, and if you flip it, what you'll see is the CO2s cancel out and the O2s cancel out, leaving you with just this. So Hess's law, I know I'm going really fast. It's just the sum of the two. This will give you, why am I doing H? I don't know why I put H here. I'm not doing H. We're just used to doing Hess's law with H.
-3.
You actually typed it. Okay, now this is,
The number is still afterwards.
so going from diamond to graphite is a very spontaneous reaction. Now, the lower the G value is, the less it's favored. So this is product favored, but it's not significant. Also, a change in G does not tell us how fast something reacts. It does tell us it's going to react without help, but doesn't going to tell us how fast something's going to react. Okay, so there are some limitations to change in G. It does tell us it will definitely react on its own, and how far right or how far left it is, but it isn't going to tell us how fast. Because we know that diamond does not spontaneously happen fast. Whoopsies, I went the wrong way. Okay, the last way, I think I might have had another example in here. That's the methanol one. Okay, yep. So, since it is a state function, we can also use, probably the easiest of the three ways, is this way. Products minus reactants. So if I know the Gibbs free energy of the reactants, and I know the Gibbs free energy of the products, I can just solve like I would do change in H and change in S from the data in your appendix. Okay, you've got a G column there. This is probably the easiest of the three. So why don't you guys do this? I think you guys can figure this out. You know what I'm saying, right? When I say products minus reactants? You guys all understand that?
What was it that we did? Where it was like something, it was like reactants minus compounds. What was that?
I do vaguely know what you're talking about. Why can't I figure out?
Wait, what reaction?
Yeah, what
Oh, it's the next.
Is
Yeah.
it
That one. The methanol one, I think it's methanol.
Can you do any of these, or is it based on what information you
Yeah.
get? Can I just use?
Well, yeah, well, it is based on what information they give you, yes. In theory, I think you could use the easiest one.
So change
But there are definitely, because you have all the G values here in the back of your book, they might have strategically left out some G values, and then or gave you homework questions where they you don't have the G values in the back of the book, so you have to do it a certain way. That's very possible. But in theory, you could use all three. But it does kind of depend upon what they give you. Like if they give you steps, they don't give you the steps, you can't use Hess's law, right? But if they do give you the steps and the final balanced chemical equation, you in theory could use the first and the third as well. You wouldn't have to do Hess's law. However, what I would do is I would probably try to do the one that they are trying to get you to do. Where's the fun in that? Thing is that if you just do this last way, products minus reactants, you may be unprepared to do the change in H, change in S way. Good. You did that? Yeah? Any? Okay. And is that spontaneous or not? Okay, but the limit